This fifth lecture on Fourier series, we shall consider few more examples of Fourier series. As the fifth example, we consider f of x is equal to cos of alpha x and is defined between x is equal. If alpha is not an integer, then even if c is equal to pi, the circle is not completed as shown in this figure. Here we have considered alpha to be 0.8 and c is equal to pi. This is the nature of the graph and this is the first derivative. It is found that cos of alpha is continuous, cos of alpha x is continuous while its first derivative is not continuous. And furthermore, the function is even if we define in C. So f, this is even, and we need to calculate only a n. So bn's are 0. A0 is defined as 2 upon 2c into f of x dx from 0 to c. So this will come out to be 2 by c cos of alpha x dx from 0 to c. And the result is 2 upon alpha c sine of alpha x from 0 to c, and this is 2 by alpha c sine of alpha c. If alpha happens to be an integer and c is equal to pi, then it is of the form m pi and is going to be 0. A n is equal to f of x cos of n pi x by c dx. This is equal to 2 upon c cos of alpha x cos of n pi x c dx integrated from 0 to c. This we write 1 upon c integration 0 to c cos of n pi c plus alpha x dx. We further write it as 1 upon c this, and simplify this as cos of n pi alpha c by cx plus cos of n pi minus alpha c by cx dx from 0 to c. You see, if alpha c happens to be an integer, then this part only contributes and the result is 1. Now if we integrate this, we will have c, this cancels with this, and we will, in the denominator we will have n pi plus alpha c, and this is sine of n pi sine of n pi alpha c by cx within limit 0 to c plus n pi minus alpha c sine of n pi minus alpha c by cx within limit 0 to c. The lower limit gives you 0 result. Note the correction over here. The lower limit gives 0 result, so we will have this. If we put x is equal to c, this is in the numerator, we will have sine of n pi plus alpha c, and in denominator it is n pi plus alpha c plus sine of n pi minus alpha c divided by n pi minus alpha c. Now it will have two terms, sine a plus b. So sine a cos b, sine a part is 0 because sine of n pi. So the second term survives. So the first will have cos of n pi sine of alpha c by n pi alpha c, and from this part it will be negative. For cos of n phi is to the power minus 1 to the power n sine of alpha c, and in the denominator we will have n square pi square minus alpha square c square, and then we will have twice alpha c. So the final result is minus 1 to the power n twice alpha c sine of alpha c n square pi square minus alpha square c square. This is the final result for an. You see that the function is continuous, its first derivative is discontinuous, so the independence is in the form of n square. And another thing, if we have alpha c is equal to m pi with m belonging to integer, in that case the result is 0, but this is not the correct representation. If this condition is satisfied, then this term do contribute, then we will have an is equal to 1 upon c, then integration 0 to c cos of n pi minus m pi c by x dx, and this is equal to c times delta mn, so 1 by c times delta mn. So this is only m part will survive, and in that case an is equal to am and is equal to 1, and all other ans are equal to 0. And similarly for a0 is 0 2. So we see that if we have e to the power mx function expanded, then it will have a single term as expected. And for non-integral values of the alpha, non-integral values of alpha will have a series of components. Similarly, another example that could be of interest is the sixth example is the sine function. Again, in the case of sine function, we will find the function itself has a discontinuity. But its first derivative, the cos, is continuous. So we expect that if we consider f of x is equal to sine of alpha x with x in a symmetric interval, this is the, in that case we see that the function has this form while its first derivative has this form, and we calculate this is odd, so only bn to calculate, and bn is equal to 2 upon 2c into c f of x sine of n pi x c dx from 0 to c. And we see that this is equal to 2 upon c, and this is sine of alpha x sine of n pi x c dx from 0 to c. So this can be written as 1 upon c just as in the previous case, only note the relative magnitude, relative signs of these two terms. And when we integrate, this c cancels out, we will have in the denominator n pi minus alpha c, and in the numerator we will have n pi minus alpha c upon putting the proper limits. This is minus 1 to the power n sine of alpha c times on simplification this comes out to be 2n pi alpha square c square. Now the n dependence goes as 1 by n because there is an n factor in the numerator. As the last example, we shall consider e to the power, when the function is an exponential function, so e to the power alpha x type function. So for example 7 is f of x is equal to e to the power alpha x, and x is defined again within a symmetric interval. The function doesn't have any definite parity, have no parity. So task is complicated. We have to calculate all ANs and BNs. A0 is equal to 2 upon 2c minus c2 plus c fx dx. So this is 1 upon c e to the power alpha x dx from minus c to plus c. So this is 1 upon alpha c e to the power alpha c minus e to the power minus alpha c. We may write it in terms of sine hyperbolic also. AN we integrate it in parts. So first thing is the factor that will come out c upon n pi. So this is 1 upon n pi, and then we will have e to the power alpha x sine of n pi x c, and then we will have minus alpha e to the power alpha x sine of n pi x c dx. Both from all the quantities are in the limits from minus c to plus c. We integrate it once again in parts. So the first part is 1 upon n pi is out, then we will have e to the power alpha x sine of n pi x c, and from this minus alpha is common, and then whenever we integrate this we will have altogether alpha c upon n pi, because minus alpha by n pi will come, and there were already minus alpha, so altogether it is alpha c upon n pi with a positive sign. This is this term, and we will have e to the power alpha x cos of n pi x c minus alpha e to the power alpha x cos of n pi x c dx. You see that this is nothing but the definition of AN itself. So we write it like this. This term has 1 upon n pi e to the power alpha x sine of n pi x c, and this term has plus alpha c n square pi square e to the power alpha x cos of n pi x c, both is within the limit from minus c to plus c, And finally this term, this is alpha square, n square pi square. So this is minus alpha square c, alpha square c, n square pi square times from minus pi to plus minus c to plus c. If we look at the definition of an, there were 1 by c, so this part can be written as alpha square c square by n square pi square an. So we take it on the other side, so we'll have 1 plus alpha square c square by n square pi square an on the left, and on the right hand side if we put the value, this is either sine of n pi or sine of minus n pi, so it doesn't contribute, so this goes. And for this part it is alpha c upon n pi, so alpha c upon n square pi square, and we will have e to the power alpha c cos of n pi minus e to the power minus n pi cos of alpha c, sorry, cos of n pi, cos of n pi being minus or an is equal to, this goes, this is equal to minus 1 to the power n minus 1 to the power n alpha c, alpha c e to the power alpha c minus e to the power minus alpha c, whole thing is divided by n square pi square plus alpha square c square. This is the expression for an. Similarly bn can be calculated. If we carry on calculation in the same line, bn will come out to be minus 1 to the power n pi e to the power alpha c minus e to the power minus alpha c by n square pi square plus alpha square c square. By this example we stop working out examples any further, and we shall, from the next class onwards, we shall again come to the theory of Fourier series. So up to this lecture, what we have done, we have first discussed Dirichlet's condition and orthogonality of sine cosine function over the period 2 pi. Then we have stated the Fourier theorem and its simplified versions for even and odd functions, and we have considered a lots of examples, 7 examples. In the first from the first examples we concluded that the nature independence of the expansion coefficients has direct relation with the order or with the discontinuity in the derivatives or function itself.